You know when you're at the store and you see a carton of pure milk or a box of pure spices? We use that word pure all the time, right? It usually means something's natural or healthy or that nothing extra has been added. But what if I told you that to a scientist, almost none of those things are actually pure? Seriously. So come on, let's peel back the label and see how science completely redefines the very stuff our world is made of.
So here's the game plan. We're going to start with that milk carton to really get this purity paradox. Then we'll build out the two biggest categories scientists use, pure substances and mixtures. After that, we'll dive into the wild world of mixtures, check out the building blocks of pure substances, and then at the end, we'll put it all together into one complete map of all matter.
All right, first up, that glass of milk, the salt on your table, the juice in your fridge, are they pure? Well, it turns out the answer totally depends on who you ask.
No, really. Think about it for a second. When you see pure on a label, you're probably thinking it's fresh, right? No weird additives, just the good stuff. And you know what? In an everyday sense, you're not wrong at all. But in science, words have super specific and sometimes pretty surprising meanings.
And this, right here, is the heart of the whole thing. To us, pure just means no junk has been added. But to a scientist, pure means a substance is made of only one single type of particle. That's it. So your milk? It's actually a super complex mix of water, fats, proteins, sugars, minerals, you name it. So scientifically speaking, it is not pure at all. It's actually a fascinating mixture. This difference is basically the key to how scientists organize, well, everything. The very first question they ask about any substance is it a pure substance or is it a mixture? Let's break that down. Okay, so a pure substance is something that's the same all the way down to its tiniest particles. Take a grain of sugar. Every single particle in that grain of sugar is chemically identical to every other one. You can't break it down into simpler stuff using physical methods like filtering or anything. Its nature is just fixed. Now, on the flip side, a mixture is what you get when you just combine two or more of those pure substances. The air we breathe, the soil under our feet, seawater. Pretty much most of the stuff around us are mixtures. The key here is that the parts are just physically hanging out together, not chemically bonded, which means you can often separate them back out. And even mixtures come in two main flavors. If you dissolve salt and water, you get a homogeneous mixture. It looks and tastes the same everywhere because the particles are evenly spread out. But if you mix oil and water, well, you get a heterogeneous mixture. You can literally see the different parts, and its composition is definitely not uniform. So let's zoom in a bit, because that difference between uniform and non-uniform gets even more interesting when you look closer. We're going to get into three really specific types of mixtures: solutions, suspensions, and colloids. First up, we've got solutions. These are the perfectly homogeneous mixtures. The stuff that's dissolved in them is made of particles that are so incredibly tiny, we're talking smaller than a nanometer, that they're totally invisible and they'll never, ever settle out. Soda water is a perfect example. You can't see the carbon dioxide gas, but it's completely mixed in there. And hey, solutions aren't just liquids. The air you are breathing right now is a fantastic example of a gaseous solution. As you can see, is mostly nitrogen and oxygen with some other gases thrown in, all mixed perfectly at the particle level. It's totally homogeneous. All right, let's jump to the complete opposite end of the spectrum. Here we have suspensions. Think about mixing flour or chalk powder in water. This is a heterogeneous mixture. The particles are big enough to see, they make the water all cloudy, and if you just let it sit, they'll eventually all sink to the bottom. It's unstable. Okay, now, in between those two extremes, we find something really, really cool: colloids. A colloid, like milk or fog, is kind of the great pretender of the chemistry world. It looks totally uniform to the naked eye, and the particles don't settle out. But it's secretly a heterogeneous mixture with particles that are just large enough to do something amazing with light. This table just lays it all out so clearly. Look at the properties. Solutions: homogeneous, teeny tiny particles, totally stable. Suspensions: clearly heterogeneous, big particles and unstable, they settle. And then there's our tricky one, the colloid. It looks homogeneous and it is stable, but its particle size is in that Goldilocks zone, that just right size to do something unique, scatter light. And this unique property has a name, the Tyndall effect. And here it is. This is the perfect picture of that effect.
In a true solution, like on the left, a beam of light just passes straight through. You can't even see it. But on the right, those beautiful sunbeams you see shining through the trees in a forest, that is the Tyndall effect in action. The tiny invisible droplets of water in the mist are colloidal particles, and they are scattering the sunlight, making its path visible. It's the same reason milk looks white, and it's super important for things like paint, mayonnaise, and even our own blood.
Okay, so we've pretty much sorted through the entire complex world of mixtures. Now, let's go back to that other big category, the fundamental building block world of pure substances. So, the absolute simplest kind of pure substance is an element. An element is a basic form of matter that you just cannot break down any further by chemical means. Think of gold, oxygen, iron. These are like the universe's primary Lego blocks. Everything is built from them. A compound is what you get when two or more of those elements form a chemical bond. And the key phrases here are chemically combined and in a fixed proportion. Water is always two hydrogen atoms bonded to one oxygen atom, H2O. Always. This chemical bond creates a brand new substance with properties that are totally different from the original elements. This little experiment shows the difference perfectly. Okay, so in step 1, we just mix iron and sulfur together. It's a simple mixture, and a magnet can still pull the iron right out, no problem. But then, in step 2, we add a bunch of heat, which forces a chemical reaction. This forges a totally new substance, iron sulfide. And now look at step 4. The magnet doesn't work anymore. The iron has been fundamentally changed. It's now part of a completely new compound with new rules. So, to recap, the crucial difference is this. A mixture is just a physical mashup. It keeps the properties of its parts, and you can separate it with physical methods. A compound, on the other hand, is a new chemical creation. It has a fixed recipe, totally new properties, and you can only break it apart with another chemical reaction. Wow, we have covered a lot of ground, right? Distinguishing between all these different types of matter. So now, let's zoom all the way out and put all these pieces together into one clear picture. And here it is, the complete map of matter. Everything starts at the top, and it can only go down one of two paths. On one side, you have pure substances, which break down into either fundamental elements or chemically bonded compounds. On the other side, you've got mixtures, which can either be those uniform homogeneous ones or the chunky, non-uniform heterogeneous ones. Every single thing you can touch or see fits somewhere on this map. So here's my challenge for you. Look around your room. Right now, that wooden desk, the glass of water, the metal in your phone, the air you're breathing, they aren't just things anymore, are they? They are compounds and solutions and elements and mixtures. By understanding this map, you've literally unlocked a new way to see the world. So what do you see now that you didn't see before?